Okay, I think this actually completed our 1 electron problems, and we eventually moved to many electron problems, and from where I will actually start. Although we did a little bit of many electron problem, this course I will repeat many of the things that we did for many electron problem. So for the many electron problem, I first said that we need methods which are approximate, because the problems cannot be solved, and just as I told yesterday, because of a term which is called 1 by Rij, and I don't know if I mentioned yesterday, but the many electron problems, let us say 2 electron H of 1 not 2, if you write down the Hamiltonian, you have a kinetic energy of the electron 1. Remember the helium problem that we did, the kinetic energy of the electron 2, again I am writing these in atomic units, so these are all in atomic units, so I don't write H cross mass etc. Of course it is a reduced mass actually, but that is okay. And then you have what is called the nucleus, so Z divided by R1 minus Z divided by R2, where R1 and R2 are distances, plus 1 by modulus R1 minus R2. And we noted that, so this is for the helium atom, so in particular for helium atom, but in general we can write for any molecule or so. We noted that a part of this Hamiltonian can be written as a sum of 1 electron and 2 electron Hamiltonian, uncoupled, which means I can invoke the non-interacting theorem to solve that Hamiltonian, the wave function being product, energy being sum. But the problem really is this part, that this is a part which cannot be split as a function of 1 and function of 2. Mathematically it is not possible. So you cannot write this term 1 by modulus R1 minus R2 as any function of R1 plus any other function of R2, let us say F1 or F2 in general. So this is not even possible. If it was possible mathematically, then I would have put this R1 function with 1, R2 function with 2, and the entire problem would have been exactly solved. So the crux of the problem is that this is not even mathematically possible. Of course, lot of people have made attempts to write, can I write this as f of R1 plus some f on R1 plus f2 of R2, but it is not simply not possible. You can do a good job of it, but that is an approximation. So this is where the problem of many electron theory starts, that I can't solve it exactly. So many of these solutions have to depend on approximate methods, and two very important approximate methods that we did were actually variation method and perturbation method. Again I remind you, I have done this in great detail, so I don't know whether I should again do in the same detail in this course, but probably I will do this, because that is I think the important part. When I start, I will at least repeat most of the things. These are two very important approximate methods which are actually used to solve the many particle problems. There are many other schemes, but the helium atom is an example, but you can have any many particle problem like hydrogen molecule, any other molecule which has more than one electron. You will end up with a problem where there is a term which is a non-separable term, which cannot be written in this manner, and hence the problem is not exactly solvable. So I might mention that this is where the basic problem of solution of stationary state of the Hamiltonian starts. Although I told you, although we are interested in solving only the stationary states of the Hamiltonian, even that solution is not possible. So what we will be discussing further in this course is how to solve for many electron problem H psi equal to E psi. And this has been the quantum chemistry for 70 to 80 years. How do you solve H psi equal to E psi for many particle problem where Hamiltonian is non-separable? So far the problems that we have been doing were trivial problems. We learned a lot of quantum mechanics, but the solution of H cycle T cell was a trivial problem. I mean, some mathematical exercise. Of course, I'm not saying they're trivial, but some mathematical exercise, but doable exercise. When you scale particle in a box from 1D to 2D to 3D, they were uncoupled, so there was no problem. When you scaled harmonic oscillator to 1D, 2D, 3D, they were uncoupled. For the hydrogen atom, even for the hydrogen atom, this solution could have been done, and it was not very difficult to do this. The problem came when we actually want to solve the many particle problem, where there is a genuine term which is non-separable, and hence the problem can actually not be solved. So we have to resort to approximate methods, and the two approximate methods that we discussed were variation and perturbation. And we have to see how to integrate each of these approximate methods to make solutions from this. So this is where we'll start. We'll also look at what kind of symmetry the wave function should have, and this is something again we have said in the last class, that they must be either quantum particles must be either bosons or fermions, or electrons or fermions. The antisymmetry, Slater determinant, we have done all that up to that point, but I think we'll revise this very quickly. All right, so we'll see how to handle this problem, because that's always, this heterogeneity is always there, but we'll try to see, because then I could start, but maybe I will lose another 1 or 2 classes to bring you up to that point. That's okay, I will do that in the next class. So anyway, today we'll close. All right.